All right, so a lot of what we've just been talking about, we talked about DC current and then AC current, so the direct current and the alternating current. And now we need a way to actually convert that alternating current to DC current, because we just figured out how to generate a lot of power using from alternating current. We don't have to do it with chemical reactions like in batteries, but a lot of the devices we use run on batteries, and so they therefore want DC current. But we have to be able to plug them in case the batteries run out or to recharge them and things like that. So we need to be able to turn AC current to DC current. So that's what we're going to talk about in this one. It's called rectifying current, AC to DC. So that's rectifying current. All right, so current rectification or rectifying current. That's what we're doing here. And thankfully, we have a very nifty type of device called a diode. It's pretty interesting little device. It's made out of an N and P type semiconductor. So if you ever want to, you can look that up and see kind of how they work. But it's a little how they actually do this and how they actually work is beyond the scope of this class. But if anybody ever has any real questions you want to talk to me about it, I can go through it with you in person. But I'm not going to cover it here in the video. But basically, we have an electrical symbol for it. It looks like this. It's like an arrow with a line on the front of it. And the interesting thing about these diodes is they allow current to go in one direction. So like current could flow this direction, right? But current could not flow in this direction. So not in that direction, but yes, it can flow in that direction. And so this is our key to rectifying current. And in fact, a single diode like this is what is called a half wave rectifier. Okay? And if you think about it, if we send an AC current through this, right? So we have some AC current attached to this alternating current, and we send it over here, what's going to come out on this side? Well, if we look at our input, right? This would be our input, an AC signal, something like this, going up and down and up and down and up and down like that. What's going to happen is, let's say we have the diode in such a way that this positive current here, that can go through, but none of this negative can. So this is our normal signal, right? This would be our input. What would we get after that diode, after that half wave rectifier? What would the output be? Well, essentially, any current that was in the direction that the diode is pointed would be fine. So that first part, all fine. The current can flow. But then we get right here to this down, this negative part. And this is current flowing in this negative direction right here that it can't go. And so that's just going to get cut off. There's going to be no current flowing. And then it's going to come back up here and go across the positive side again. And so we're going to get the positive current again until it tries to go in the opposite direction and it gets cut off. And then the positive direction again and then cut off. And it goes on like this. And you can see why it's called a half wave rectifier. It basically cuts out half the wave. It cuts out this whole bottom half of the wave and just leaves you these that were in the direction of the current. Now, if we turned this diode around, then we'd have the bottom half of the wave and it would cut off the top halves. Okay? So it just depends on the direction that this is pointed, but that's why it's called a half wave rectifier. So that right there automatically takes our alternating current, where it goes one left, right, or back and forth, and changes it into just a current that basically turns on and then off, and then on and then off, and then on and then off. But the problem with this is, yes, this is now DC current. Here it was AC, but now here it's DC. The problem with this is we're wasting a lot of energy. Like half of our energy here, all this energy we spent in producing all these negative direction currents, all the back ones, we're just cutting it off. We're getting rid of it. So we can come up with a better way to do this, and this requires 4 diodes. This is called a full wave rectifier. And so what you do is you have to set them up in a manner like this. Trying to draw this as neatly as I can here. And then that. And so this will be our full wave rectifier. And what we'll do is we'll have our output here. Our output's going to come like this. Okay? So I'm going to put just little circles here. This is where we could attach a voltmeter or some device that needs DC current. We could attach it right to here. And then our alternating current source would be over here. Here's our alternating current source. And then we're going to send it in right to here and right to here, like this. Of course, these two lines not connected. One is just going over top of the other one. This is not a short, just make sure you know that. So we have our AC source. And if we look at what happens, you can see that when current starts off going this direction, right? Current goes around here and it reaches this corner, this little node here. And it can't go down left. It cannot go this way. Can't do that. But it can go this way, which means it'll come over here, go through that, come out this way, come through whatever device we have attached here. I guess I could put something. All right, we have some sort of a DC device attached here, right? So this will come down here. It'll go through the DC device, right? Go through, get used up, come back around this way, go up, then it gets here, and now it doesn't want to go this way because this is back to that same voltage that it was at. So the voltage here keeps it from coming up because this is the high voltage. So it comes down this way, right? I know it can go in the direction of that diode, but if it tries to, the voltage keeps it from going there. It can come down this way, it can go through this diode. Again, this going this way takes it back to that high voltage. It wants to go to low voltage, so it comes around, goes down, comes up this way, and goes back. And it's made one then full loop. Then, when it flips and the current goes this way, right, it's going to come around. Maybe I should draw that red one, the path a little better. So the red path is this way, down over this way, through our device, back over this way, up, around this way, and back over. Okay, and that's our direction right there, up here. Okay, it's going this way, down here, over here. Okay, up here, back around, and over this way. Okay, so that's the red path. And then when the current flips and goes the other direction, it can come down this way. It's going to come across just like this. It's going to get here. Now it cannot go this way, but it can go this way. So far we've come this way, and then we're going to go up this way. And then now look, we're right going through the DC the exact same way that the red current did when it was flipped the other way. It's going to come around, still following that DC direction. This time it's going to come up here, and it doesn't want to go back here because that's back up to the higher voltage now. It's going to come out this way, up and over, and back in. So on this side of the circuit, the alternating circuit part, the red and the green are always in opposite directions. It's as it goes back and forth. So it flows in the red direction, so it flows like if we looked at this video, this would be the green. This would be the green part, right? When it's flowing in that direction, and this would be all the red direction. So it flows in the red, then flows in the green, then flows in the red, then flows in the green, then flows in the red, and so it'd go red around this way, up around, and then it'd start to flip and go green would come up around this way and go back around, and it would just keep going back and forth. But no matter what, when it reaches this DC part, the red and green are both going the same way. And so what this does, this full wave rectifier, what it does is it rectifies both sides of the wave. So this, with one single diode, with our half wave turned into this. For this, the output is going to look like, hopefully you can kind of guess this, it's going to look like this. It makes both the positive and negative currents just become the positive direction current, and we get that kind of thing. All right, and so now we have this thing fully rectified. We're not losing any of that energy. But, but we still have a little trouble here with the shape of this. It's still current on, and then it goes off real quick before it comes back on, and it goes off quick. Here it was staying off for half a cycle and then coming back on for half a cycle. But here it's still turning off. and off, and off, and it's still off and on. It's just off and on a lot faster without any, when it's, long periods of it staying off. But we can even do actually a little better than this. And we haven't exactly learned about capacitors yet, but if we take this whole full wave rectifier, right, so just sketch it real quick again here. If we take this whole full wave rectifier, all right, so here's our full wave rectifier. Here's our output. Here's our alternating source, right? So this whole thing, we take that, and what we can do is say, here's our outputs. Well, what we're going to learn about in the next section are capacitors, and we'll learn more about how they work. But just so you know, after you watch the capacitor video, come back and look at this part, and you should understand why if we take a capacitor, and this is the symbol for a capacitor, two parallel equal length lines, so it's not a battery. Remember, the battery was a long line and a short line, or the cell was long, short, long, short. This is just a single capacitor. It's two parallel lines that are the same length, and it stands for a parallel plate capacitor, which again we'll learn about in the next video here. So come back after. But I got to talk about it here because it goes with this rectification thing. If we short this out with a capacitor whose capacitance is C, which again I'll define in the next video, well, what happens is this capacitor, it takes time to fill up. So when current comes down through here, at first it acts like it's a short, and the current just flows through it, but then it fills up, okay? And then once it fills up and you try to switch the directions, it doesn't let you switch directions real quick. Like if you try to turn the current off, so what'll happen is current will come here and it'll go through our device, our DC device, okay? But also some of it comes down here and fills up on this plate, and it stores the current here. And then when the current goes to this little point where it's turned off here, right? What happens is the current will come back out of this capacitor and go through our device. It's like it fills up and then it comes over here and comes back out. It's almost like you turn the sink on and you have it run some water, and while it's running water, you simultaneously have it fill up a water balloon. So half the water goes into running water and the other half goes into filling up a balloon. And then if you turn the sink off, you can then use that balloon and start emptying that balloon and still have water flowing. Okay, the water balloon. And it's kind of like that, so that it fills up on one side, and then when the current turns off for this balloon or starts to decrease, this starts to send out the DC current in that direction. It starts sending it back out, so the current doesn't totally shut off. And then when the current flips the other way, it does the same sort of thing. This discharges, and then of course when the current flips and starts to come back on, it starts providing the DC current through here and starts refilling the capacitor back up. And then when the current starts to flip off, the capacitor discharges and keeps the current going. And then when the capacitor starts to run out, this goes back up on an upswing and starts refilling the capacitor and keeps the DC current going. And so what happens is, and I'm going to draw this a little bigger because and we'll learn about how capacitors discharge, but we take something that looks like this kind of, this full wave rectified thing. And what happens is when we get to this point and the current starts to go to zero, the capacitor starts kicking in and it discharges slowly, and it does something like that. And so what happens is you get your current, instead of it going down to zero, what happens is your current comes up like this and then cuts over. And you eliminate this part where it drops to zero. And then it goes back up, and then it cuts back down during the capacitor's part while the capacitor keeps the current going. And then it goes back up like this across the top, and then it cuts back down like that. And so what you end up with is you end up with a current that's a little bit kind of wavy. I didn't draw that well. It's like an arch, and then it cuts down, and then an arch, and then it cuts down, and then it arches and cuts down. And so you get something like this, but it's a lot more steady than this, right? And depending on the capacitors you put there, you can actually change this. In fact, the couple things that matter about this is the bigger the capacitor, bigger C, means it's going to be smoother. So a small capacitor, you might end up with something that curves and drops down a lot and then curves and then drops down a lot and then curves. But with a bigger capacitor, you might be able to just kind of have just a little bump in the road kind of thing, and it's going to be very, very smooth. The second thing that affects it is a small load. That means that if this guy right here isn't using up a lot of the current, then a lot of it can go into filling up this capacitor. And so that when this goes to one of its shifting off periods, the capacitor has a lot of charge, it can go ahead and keep sending over here. And this thing doesn't even need a lot, so it doesn't even have to have a lot. So it can fill up more, and then it also doesn't have to provide as much during the low points. And so a smaller load means smoother as well. So those two things will help with it. All right. I think after the next video on capacitors, what I was just trying to say to you here will make sense. Pay attention in the next video on how capacitors discharge, because they discharge exponentially. So this little curvy down part would actually be like what happens with a capacitor, because a capacitor discharges down like this, like exponentially. And so that's the little part you're getting there. You're getting a little bit of this little exponential curve down, and if you continued it on up, you would see that it was like this. You could see that it's just that little part of that exponential curve like that. It's getting kind of messy, so I'll stop there. I'm going to kind of quit while I'm ahead because I'm not drawing this very nicely. Take a look in your book and you'll see better pictures than what I'm trying to draw of it. But that should pretty much be it for rectifying current. All right.